Alright, so here we have a block of mass M1, which is 10 kilograms at rest on an inclined plane. That makes an angle of 15 degrees with the horizontal. And this is the coefficient of friction between the block and the inclined plane is 0.3. This is a massless, inextensible string. It's attached to one end of the block. It passed over pulley 1. Here's pulley 1, where my cursor is tracing out. And this is around a second free pulley, or free suspended pulley, which is this one is labeled pulley 2. And it's finally attached to a fixed support. The fixed support is up here. And so the pulleys are massless, but a second block of mass M2, which is 12 kilograms, is hung from the suspended pulley. So here's M1, here's M2. M1 is sitting on an inclined surface. It is rough because the coefficient of friction is given us as 0.3. And it wants us to calculate part A, B, and C. Okay? All right. So for these free suspended pulley, this type of system, it is important that you recognize which one accelerates faster and which one accelerates slower right away as you practice. The mass that's attached to the quote-unquote free suspended pulley will always accelerate slower. So in this case, M1 is going to accelerate faster. M2 is going to accelerate slower. At what rate? The ratio is always going to be a 2-to-1 for these types of diagram. Here's M1. It is going to accelerate twice as fast. And then M2 is half as fast as M1. In the same amount of time, M1 will cover twice the distance, while M2, the hanging mass in this diagram, it is going to accelerate at half the rate. So therefore, accelerating at half the rate in the same amount of time will result in half the distance traveled. Okay, so keep those concepts in mind. If you need to, rewind the video and listen to that again. All right, let's go and crack this out. Before you attack A, B, and C, I think it's super important to draw your free body diagram out so that 1, you account for all the forces that are present in the schematic. 2, you don't forget anything. All right. So in no particular order, I'm just going to go from left to right as I usually do. Here is for the inclined plane. Here is your coordinate axis. Here's the y-axis, and then here is the x-axis. Once again, we take the x-axis for ramps to be along the surface of the ramp, and then therefore the y-axis needs to tilt with this system. So the x-axis is the surface of the ramp, so therefore y-axis has to be perpendicular to the ramp, so it's going to be tilted with it, like I said. All right, let's go and identify our forces for M1 because it's resting on a surface. It has an F of G pointing down the page. Here I'm just going to call it F of G1 because F of G here is now in between the x-axis and the y-axis. It has to have components. Here is F of GY, here's F of GX, and the angle given, which is 15 degrees in the statement up here, it says makes an angle of 15 degrees with the horizontal. So here's theta. This theta is the same as this theta where my cursor is resting. Okay, so keep that in mind as you practice incline. Hopefully by now your angle for inclined surfaces is pretty solid. If not, hopefully watch other videos. So here I've labeled this angle that is touching the F of G1 vector to the F of Gy vector. That is the same theta as the theta that's touching the horizontal axis here in the original schematic. Here, F of Gy, or F of G1, y, is mg cosine theta. It's cosine because this dash component, it is the adjacent to this leg. So hence, adjacent is cosine. And then the next component is F of G1x. F of G1x is mg1 because we're looking at mass 1. And then that's going to be sine of theta. Sine because this is the opposite leg referencing this theta. Okay, so this is theta. That's your opposite. So opposite in here, that'll be sine. Sine is opposite over hypotenuse. So F of G1x is m1g, which is the hypotenuse times sine of theta. All right, let's go ahead and identify our other forces. This is F of n. Because the box is resting on an inclined surface, there has to be an F of n or a force exerted by the surface onto the box. So that is F of n. But keep in mind that F of n for this particular problem, right, not all the time, but for this particular problem, the way it's drawn here, F of n has the same magnitude as F of G1y because I see one vector pointing down along the y-axis and there's another vector pointing up along the y-axis. And because net force in the y direction is 0, it implies and suggests that Fn here, or you can call it Fn1 if you want. This hanging mass has no Fn, so I'm just going to call it Fn. And then that is equal to F1g, or Fg1y, okay? So the two vectors along the y-axis must equal in magnitude. Opposite direction though, all right? Here, f of 2, because it is the hanging mass, it has to have a f of g, or weight, pointing down the page. So I'm just going to call this f of g 2. Since we have m1 and m2, I'm just going to differentiate the weight, or the f of g, here by subscript 2. Next thing you should identify is the tension in the string. Here I only see one string that's connecting m1. It wraps around this fixed pulley, and then it's wrapped around the suspended pulley, and then it's hooked up to the area where it's fixed, okay, this fixed support. All right, so therefore, if this is T and there's only one tension, if you look at the suspended free pulley 2 in this diagram, there has to be 2 tensions that's pointing upward, because as M2 is falling downward, there is 2 opposing forces that's slowing down, and that is because of the way the system is designed. All right, so this pulley has a string that's wrapped around it, but this is T pointing up, aka slowing it down, and this T is also pointing up because it's slowing it down. So therefore, the opposing forces for f of g2 is these, or are these 2 T's pointing upward. All right, and then last but not least, don't forget, because it gives us the coefficient of friction for the inclined plane. I know right away there is some sort of frictional force exerting on the box from the surface of the box in the inclined plane. So in this case, the system is going to move up the ramp, because M2 is 12 kilograms and then M1 is 10 kilograms. This hanging mass will generate a large weight compared to what M1 is going to do, aka in terms of f of g1x, because it's only 10 kilograms. All right, but honestly, it really doesn't matter. If you're just looking for the magnitude of the of acceleration, the magnitude of t, you can actually assume that m1 goes down the incline, m2 would then go up, because as long as you're consistent, the magnitude will always be the same. Okay, but in this case, I know m2 is going to pull the system to the right, or aka m2 is going to go down. Therefore, m1 has to go up the ramp. All right, so I'm going to call this vector here f of k, because f of k in this case opposing m1's motion, and m1 is going to go up the ramp, so therefore f of k points downward. All right, here I'm going to set up block 1 and block 2 with the information here. If you haven't seen the other videos, this is important here that you realize just by looking at it. As I stated at the very beginning of the video, m1 in this case will accelerate faster than m2. Okay, well, how much faster? Twice as fast. Because the real life scenario, if you were to set up the system and if you actually measure the distance, it will give you a 2-to-1 ratio, which suggests that m2 will travel twice the distance in the same amount of time. And because the system starts at rest, it implies that m2 actually only travel half the distance if you were to measure it. So here in my work, I have a1, which is for the block on the inclined surface, accelerates twice the rate of a2, which is the hanging mass here, which is attached to the suspended pulley. Or the other way to look at it, if you wanted to, you can say that a2 is half as much as a1. So pick a perspective that you're comfortable with and stick with it. Okay, but the most important part is to be able to look at a diagram and figure out which block or box or mass accelerates faster. So as you practice, keep that in mind. Here, I'm just going to do f of 1. Part A asks us to calculate the magnitude of the acceleration m1, so I'm going to find a1. So to find a1, I need to set up the net force for block 1, which is m1 times a1. Here I need to use subscripts for a, because the blocks do not accelerate at the same rate as of the pulley system. Okay, but if you look at m1, which is the block on the inclined surface, you have t that's going to pull it upward. And then you have f of gx down here, which is pointing down the slope, aka against the motion. And then in addition to that, you have f of k that's also pointing down slope. So if you look at m1, there are 3 vectors on the x-axis, t, which is going to cause it to go up the slope. At the same time, f of k points down slope, f g1x points down slope. Hence, I have t minus f g1x minus f of k. And keep in mind that I've already taken care of the negative signs here for you, okay? And that equals to m1a1. Emphasized again, for these types of free suspended pulley system, they accelerate at different rates, so you need to use subscripts for acceleration. All right, I'm just going to expand f of g1x into m1g sine theta because it says so in the diagram. F of g1x is the opposite leg of this right triangle, so that would imply sine of theta. And then f of k by definition is mu k f of n. I don't know what f of n is, but I mean, if you kept up with the explanation for these components and the vectors, here, if you look at the y-axis, Fn is pointing upward, f of g1y is pointing downward, but the acceleration in the y-direction is equal to 0, so therefore the magnitude of Fn is the same as the magnitude of F1y. So I can replace Fn with Fg1y, which is m1g cosine theta. And that's why I have highlighted here. I substitute Fn out for Fg1y. Okay. Well, you know all the values already. So if you plug in m1, which is 10, you plug in g, which is 9.8, because I've already taken care of the negative sign in the front, and then sine of 15 degrees, you'll get 25.36. And then if you plug in 0.3, which is the coefficient of friction, which is given the problem that I'm circling, that's 0.3. And then you type in mass, which is 10, and then g is 9.8, and then cosine of 15, you'll get 28.4. And then on the right side, because we're looking at mass 1 right now, that's 10 kilograms. So as you can see here, if I can simplify, negative 25.36, negative 28.4 reduces down to negative 53.76. And I highlighted the two unknowns here. All right. Part A asks you to find the magnitude of A1. Well, I need to find A1, but I don't know what T is, which is okay. As you can see, if you set up the physics now for M2, it has two T's in here, which will allow us to get rid of T. Here, I'm going to set up the physics for M2 or block 2. The net force on block 2 is equal to mass 2 times acceleration A2. But if you look at block 2, the weight of M2, or F of G2, is going to cause the block to accelerate downward, while opposing it are these two T's due to the distribution of the tension around this free suspended pulley. Okay, so here I have F of G2 minus 2T, because there are two arrows that are pointing upward, and both those arrows have the same tension. All right, and that equals to M2A2. Well, this is pretty light work, right? F of G2 is simply mass 2 times gravity, and then everything else stays the same. But mass 2 is given as 12 kilograms here, M2, where I'm cursing back and forth towards the top left of the screen. M2 is given as 12 kilograms. So if you plug in 12 kilograms times 9.8, you'll get 117.6 minus 2T times 12 kilograms. Well, what I do here is I substitute out for A2. Now, why did I do that? Part A asks you to find the acceleration of M1, which essentially implies that you need to find the acceleration of A1. Well, here I have A2. I don't want A2, I want A1. So I can substitute out A2 for A1. So A2, watch where my cursor is circling, right? So it's important that you understand these ratio between distance and acceleration for these types of systems. I know that A2 will accelerate slower for this diagram because this is the mass that's attached to the free suspended pulley. Well, how much slower? Half the rate of A1. So A1 being the faster one, you take the faster one divided by 2. So A2 here is A1 divided by 2. So now that I have everything in terms of the same variable on the left side, T and A1, I can just simplify my work. Well, 12 divided by 2 is just 6. Hence, that's where the 6 comes from. The left side hasn't changed. Okay, but what I do want to point out is that here you have a 2T. Here on the left side, you have a T, right? Well, that's pretty easy to do. So here on the left side, I want to solve for T. Well, why would I want to solve for T? I'm solving for T because on the right side, I can solve for 2T. And then from there, the algebra is pretty whack. To get T by itself, I want to move this negative 53.76 Newton to the right side. So hence, I have 10A1 plus, because moving the coefficient here because the negative to the other side, the equal sign, it changes sign, plus 53.76. Well, here I have T, right? On the right side, I can simplify this equal to 2T. So the 117.6 stays the same. This is negative 2T, so I want to move negative 2T to the right side of the equal sign, which makes it a positive 2T. But then this is 6A1. Well, to get 6A1 to the other side equal sign, I would subtract, because this is positive. So to move it, I would just subtract, okay, not divide. Please make sure you do your algebra correctly. So here in the statement, I have an expression for 2T. But here on the left, though, I have an expression for T. Well, that's pretty easy to do. I can just multiply the left side by 2. So here on the left side, I want to multiply by 2. But what I do on one side, I have to do it on both sides. So here, 2 times 10 is 20. I left the units out on the next step here just to clean it up a little bit. And then 2 times 53.76 is 107.52. Now I have an expression for 2T. I have an expression for 2t. So what I'm going to do is I'm going to set these two functions equal to each other, as I've done before in other videos. I like to find things that are similar and then set the two functions to find what it is that I'm missing. So here we have 20a1, which is carried down, plus 107.52 I carry down. Here 2t is equal to 117.6 minus 6a1, which I carry down here. As you can see here in the statement, the only unknown is a1, which is what we're asked to find in part A. Well, I'm going to combine like terms. I'm going to move this negative 6a1 to the left side, which makes it positive. And I want to move this 107.52, that's positive, to the right side of the equal sign, which makes it negative. So if you do that properly, 20a1 plus 6a1 and then 117.6 minus 107.52 will give you about 10.08. Okay, and then to find a1, we divide both sides by 26. So 10.08 divided by 26 will give you a value of 0.39 meters per second squared. And because it's this magnitude, I don't need to include the direction. I'm done there for part A. Now that you've finished part A, part B asks you to find the magnitude of the tension in the string. Well, there's only one string, right? It just happens to be distributed differently around this free suspended pulley. So I want to find part C, super whack. Part B. To find part B, it says find the magnitude of the tension in the string. There are different ways to do it. I'm just going to find T by using this function that is coming up here. I highlight this box orange because, well, I already have T by itself. Part B wants me to find T, so why not use this one, right? Because the only thing missing is A1. But I just found A1. So I'm just going to carry my work down, or to the right. Here, all I did was I rewrote this function, T equals 10 kilogram times A1 plus 53.76 up here, because T is already by itself. Well, I know what A1 is. A1, the magnitude of it is 0.39 because I'm treating the line of motion to be positive. And really, the only thing that I plugged in was A1 because I just found it. And then here's just calculator work, right? 10 times 0.39 is 3.9 because you shift the decimal one spaces to the right. And then add that to 53.76, and then your answer is going to come out to be 57.6 newtons. That's the answer of part B. So part B is super easy, but to do part B, you had to know the answer to part A. All right, now part C, it says find the distance traveled by the hanging block, M2, which is this one right here that I'm cursing, the hanging block that's attached to the suspended pulley, after 2 seconds. Well, I can just use my displacement function, right? It asks for distance. Well, distance is a scalar. Displacement is a vector, but I can just use my displacement function, find the answer, and just leave out the direction. So here, VI is 0, so I'm just going to cancel that out. So the only thing I'm going to carry down is 1/2 AT squared. But you notice here, this is A2, okay? Because it asks you to find the distance traveled by the hanging block, M2. Well, it's important that you use subscript. This is displacement for mass 2, which is the acceleration of 2 times t. But t doesn't have a subscript because the system moves uniformly as one motion, right? So both blocks share the same t. Well, here, I'm just going to carry it down. And I don't know what A2 is, right? A2, I don't know what it is because part A asks for the acceleration A1. But what I do know from my previous work, or my previous statement, is that if you look at the system, M2 is going to accelerate slower. Any mass that's hooked up to the quote-unquote free suspended pulley will always accelerate slower. Therefore, M1 in this case will accelerate at twice the rate. So I can say that A2 is half of A1 because A1 in this case accelerates twice as fast, so I can say A2 is half as fast. And half as fast would imply that you're dividing by 2. Well, this is pretty light work now. I can just plug in A1, which I found earlier, which is 0.39. The 2 stays the same, and then time happens to be 2 seconds in this one. Well, watch my cursor. 2 times 2 in the denominator is 4, and then 2 square here is 4. So square 4 in the denominator and 4 in the denominator will cancel out perfectly. So really my answer for this one is just 0.39 because, again, 2 times 2 in the denominator is 4. But then 2 square is 4 in the numerator, 4 in the numerator, 4 in the denominator cancels out. So the only thing I have left here is just 0.39, or you can just plug that in your calculator if you like. And that is the answer for part C. Okay, and that's it for this one. All right, stay nerdy, don't be whack.